We'll start in 1 minute. Today we'll continue in section 4.2, applications with systems of linear equations. So we got to number 5. Number 5 says a boat traveled 30 miles going downstream, meaning that it's going with the current, in 3 hours, and it traveled 30 miles upstream against the current in 5 hours. Find the speed of the boat in still water and the speed of the current. Okay, so this problem involves the uniform motion equation, rate times time equals distance. So I'll write that down here, rate times time equals distance. Or you might say distance equals rate times time, which is equivalent. So we have two situations. The boat is traveling downstream with the current in one case, and in the other case, the boat is traveling upstream or against the current. So we'll write down two equations involving uniform motion. One when the boat is going downstream, and the other when the boat is going upstream. And we're supposed to find the speed of the boat if it were in still water, and then the speed of the current. So remember what we do, we identify the quantities that we're supposed to find, and then we assign variables to represent those quantities. So the speed of the boat in miles per hour, I'll use capital B to represent the speed of the boat measured in miles per hour. And then the speed of the current. Speed of the current. I'll use capital C, measured in miles per hour. And we'll write down two equations, one at a time. One involving the boat traveling downstream with the current, and the other equation involving the boat traveling upstream, which is against the current. Okay, so we'll use the information given in the first part of the first sentence. And I'll amplify this by throwing in some other terms. So a boat traveled a distance of 30 miles going downstream with the current in 3 hours. 3 hours is the amount of time it takes. Okay, so if the boat is traveling downstream, then how fast is it going? Or what's the rate? Well, the rate will be faster than the boat would travel in still water. That's what the speed of the boat is referring to. The speed of the boat in still water is b miles per hour, and the speed of the current is c miles per hour. So if the boat is going downstream, the rate is b plus c miles per hour. That's the rate. And we're told that in 3 hours, the boat will travel 30 miles. So we have rate times time equals distance. Okay, the other situation, the boat is traveling upstream or against the current. So if the boat is going against the current, it has to be going slower than b miles per hour, because b miles per hour is how fast the boat can travel if there is no current. So when it's going upstream, the speed will be b minus c, or the rate is b minus c miles per hour. And we're told in the problem that when it is going upstream, it travels a distance of 30 miles in 5 hours. So rate times time is 5 hours, and the distance is 30 miles going against the current. Okay, so this is our system of two linear equations. And we can proceed to solve it using one of the methods that we learned about. So what I would do in the top equation, I would divide both sides by 3. And that leaves us with b plus c equals 10. And then in the bottom equation, divide both sides by 5, and we get b minus c equals 6. And then when we add these two equations together, the variable c will be eliminated, and we get 2b equals 16. So b is 8. That means the speed of the boat is 8 miles per hour. And to find c, we can use any of the other equations. So if I use the top equation, I'm not required to use the top equation, but if I choose to use the top equation, then replace b with 8. 8 plus c is 10. So the speed of the current is 2 miles per hour. Okay, so to summarize the results, we can say the boat speed is 8 miles per hour, and the current speed is 2 miles per hour. Okay, let's move on to the next problem, number 6. Okay, Robert began riding his bike toward a lake at 10 miles per hour. 2 hours later, Cheryl began driving a four-wheeler toward the lake at 14 miles per hour. Find the amount of time it took Cheryl to catch up to Robert. Okay, this involves the uniform motion equation, distance equals rate times time, or rate times time equals distance. So let's make a couple of observations here. The total amount of time it takes Cheryl to catch up to Robert is what we're supposed to find. But we can say a couple of things about time regarding Robert riding his bicycle and Cheryl driving a four-wheeler. Well, we can say one thing about the time. What's that? Well, at the instant that Cheryl catches up to Robert, we know that Robert was riding his bike for 2 hours longer than Cheryl was driving the four-wheeler, right? We're told that 2 hours later, Cheryl began driving a four-wheeler toward the lake at 14 miles per hour. So the amount of time Cheryl drove the four-wheeler is 2 hours more than the amount of time that Robert rode his bicycle. Okay, what can we say about the distances when Cheryl catches up to Robert? Well, we're assuming they started from the same place, and Robert started sooner than Cheryl, and then Cheryl caught up. So that must mean that the distance Robert traveled is the same as the distance that Cheryl traveled. Because they started from the same point. Robert started earlier, but then Cheryl eventually caught up. And so at that instant, each had traveled the same number of miles. Okay, so we're supposed to find the amount of time it takes Cheryl to catch up to Robert. So Robert's time and Cheryl's time. Okay, we've identified what we're supposed to find the amount of time it took Cheryl to catch up to Robert. So we assign a variable to the quantity that we're supposed to find. So you could use any letter you want. I'm going to pick capital T to represent the amount of time it took Cheryl to catch up to Robert, measured in hours, so T hours. And if it took Cheryl T hours to catch up to Robert, what can we say about Robert's time? Or how do we express what Robert's time is? Did Robert ride his bicycle more than T hours or less than T hours or exactly T hours?
More.
Okay, more than T hours. How many hours more than T hours? Okay, 2 hours more. So how do we express Robert's time, if Cheryl's time is T hours and Robert traveled 2 hours longer than Cheryl, what variable expression represents Robert's time?
2T. 2T.
T plus 2.
T plus 2. T plus 2, not 2 times T. 2 times T would be twice as much. But 2 hours more than is T plus 2 hours. So the words can help us. So 2 hours later, that means 2 additional hours. So additional hours implies that we're adding. Okay, so now we can move on to the next step. Robert's rate riding his bicycle is given. Robert's rate is 10 miles per hour. And Cheryl's rate driving the four-wheeler is also given, 14 miles per hour. So we can write down expressions for Robert's distance and Cheryl's distance. Okay, distance is rate times time. So how do we express Robert's distance? How do we express what Robert's distance is? Rate times time. What's Robert's rate?
10 miles an hour.
10 miles per hour. And how much time did Robert take to travel that distance? T plus 2 hours. So Robert's distance is rate times time, or 10 miles per hour times T plus 2 hours. And maybe I'll take a second here to show you how the units work. Robert's rate is 10 miles per hour and the time is T plus 2 hours. So that the hours units cancel because this hours is in the numerator and this one is in the denominator. Well, even though one is plural and the other is singular, they're still the same unit. Each represents an hour or hours, so they cancel each other out. And the units are miles. That makes sense because it's a distance. 10 times T plus 2 miles. Okay, Cheryl's distance. How do we represent Cheryl's distance? Cheryl's distance is also Cheryl's rate times Cheryl's time.
14 times T.
Yeah, 14 times T. Cheryl's rate is 14 miles per hour. And in T hours, 14 times T miles. Okay, so we're getting close. What can I do next? The goal is to find the amount of time it took Cheryl to catch up to Robert. So the goal is to solve for T. So now what?
Create two equations.
We can write down one equation. Based upon our setup here, we can write down a single equation and then solve for T. Okay, we observed earlier, Robert and Cheryl started at the same place, from the same point. Robert left earlier than Cheryl, but Cheryl eventually caught up to Robert. And as soon as she caught up, they each had traveled the same distance. The same distance. So what does that mean? It means Robert's distance is equal to Cheryl's distance at the instant that Cheryl caught up. So what's my equation? If Robert's distance is equal to Cheryl's distance, well, we're representing Robert's distance as 10 times the quantity T plus 2. And Cheryl's distance is represented by 14 times T. If they are equal, then our equation is 10 times the quantity T plus 2 equals 14 times T. And we know how to solve this for T. First, distribute multiplication by 10 over the binomial T plus 2. We get 10T plus 20 equals 14T. And then we can subtract 10T from both sides, and we get 20 equals 4T. Then divide both sides by 4. We get T equals 5. So we summarize what we found. So it took Cheryl 5 hours to catch up to Robert. Hey, let's look at the next problem, number 7. Hey, this one, George burned 1,600 calories in 2 hours of basketball and 1 hour of canoeing. On another day, he burned 2,600 calories in 3 hours of basketball and 2 hours of canoeing. So find the calories George burned per hour of basketball. Note that in this problem, it could have also asked for the number of calories that George burned while canoeing. And in our process here, we will probably also be able to determine that without difficulty. Okay, so find the number of calories George burned per hour of basketball. So I'll just use capital B for number of calories burned per hour playing basketball. It doesn't ask us to find the number of calories George burned per hour of canoeing, but we have to take it into account. So let's let capital C be the number of calories burned per hour of canoeing. Okay, so now we can write down two equations, one at a time. So in the first sentence, George burned a total of 1,600 calories by playing basketball for 2 hours and canoeing for 1 hour. Okay, so what equation can we write down using the information in the first sentence and our variable assignments? Okay, let's do a simple example first. Suppose I play basketball for 3 hours, and suppose I burn 100 calories per hour playing basketball. So 100 calories per hour playing basketball, and I play basketball for 3 hours. What's the amount of calories I burned? So 100 calories per hour for 3 hours.
300.
Yeah, 300 calories. So how did we get that? We multiplied the rate, 100 calories per hour, times the number of hours to find the total number of calories. Okay, so that's what we're doing here. In the first sentence, George burned 1,600 calories. We don't know what the actual number B is, but the rate is B calories per hour for 2 hours. So we can write down 1,600 calories equals 2 times B, and 1 hour of canoeing is plus 1 times C. Or you could put this in the other order if you prefer. 2B plus 1C equals 1,600. Okay, then in the second sentence, he burns 2,600 calories playing basketball for 3 hours and canoeing for 2 hours. So the other equation, 2,600 calories, 3 hours of basketball, so 3 times B represents the number of calories he burned playing basketball for 3 hours, and then plus 2 times C, that represents the number of calories burned for when he canoed for 2 hours. Okay, so this is our system. We can solve this using the addition method or the substitution method. Okay, I'm going to use substitution and solve the top equation for C. So 1C is the same as C, so all we have to do is subtract 2B from both sides. So C is 1600 minus 2B. And then in the other equation, we can replace C with 1600 minus 2B. Okay, so by substitution, we have 2600 equals 3 times B plus 2 times the quantity 1600 minus 2B. Then we just solve this for B. So 2600, and then do the arithmetic on the right-hand side. 3B, and then plus 2 times 1600 is plus 3200. And minus 2 times 2B is minus 4B. And when we combine like terms, on the right-hand side, we get 3200 minus B. Okay, the next step, we can do a couple of things at once. We can add B to both sides and also subtract 2600 from both sides. Or if you prefer, we can just subtract 3200 from both sides and we'll get negative 600 equals negative B. Either way, we're going to end up with B equals 600. And then to determine the value of C, we can use this equation and substitution. So C is equal to 1600 minus 2 times B, which is 2 times 600 or 1200. And that simplifies to 400. Okay, so playing basketball. George burns 600 calories per hour. <clears throat> 600 calories per hour. And canoeing. And while canoeing, he burns 400 calories per hour. Okay, let's move on to the next page. Okay, this one, Bernard departed a rest stop along the interstate and traveled at 60 miles per hour. 2 hours later, Elizabeth departed the rest stop and traveled at 75 miles per hour in the same direction as Bernard. Find the amount of time it took Elizabeth to catch up to Bernard. This problem is similar to the one that we did earlier with the bicycler and the four-wheel driver. Same kind of thing. So find the amount of time it took Elizabeth to catch up to Bernard. This is uniform motion, meaning rate times time equals distance. So we're supposed to find the amount of time it took Elizabeth to catch up to Bernard. So assign a variable for Elizabeth's time. I'll just pick T hours, and Bernard's time. Well, Bernard left that rest stop 2 hours before Elizabeth departed the rest stop. So if it took Elizabeth T hours to catch up to Bernard, then Bernard had been traveling for T plus 2 hours. Bernard's rate is 60 miles per hour, and Elizabeth's rate is 75 miles per hour. But by the time Elizabeth catches up to Bernard, their distances are the same. So we can write expressions for Elizabeth's distance. And also Bernard's distance. And then their distances are the same. So Elizabeth's distance, that's her rate times time. So Elizabeth's rate is 75 miles per hour and for T hours. So 75 times T miles, because miles per hour times hours simplifies to miles, right? And Bernard's distance is his rate times his time. So Bernard's rate is 60 miles per hour for T plus 2 hours. And so his distance is represented by 60 times T plus 2 miles. Their distances are the same, so we set 75T equal to 60 times T plus 2. And then we solve for T. So 60 times T plus 2 is 60T plus 120. Subtract 60 from both sides, we get 75T minus 60T is 15T equals 120. Divide both sides by 15, T is equal to 8 hours. Okay, it took Elizabeth 8 hours to catch up to Bernard. Okay, number 9. Some quarters and nickels have a value of $4.60. The number of quarters is 3 more than twice the number of nickels. Find the number of quarters and nickels. Okay, find the number of quarters and nickels. So assign variables to represent the number of quarters and nickels. So I'll use capital Q for the number of quarters. And capital N for the number of nickels. The monetary value of the quarters and nickels is $4.60. And then in the second sentence, we're told that the number of quarters is 3 more than twice the number of nickels. So from that information and our variable assignments, we can write down 2 equations, one at a time. So how about the first equation? Write down the equation involving the monetary value, or the value of the quarters and nickels in dollars. So monetary value equation. Well, the monetary value of all the quarters and nickels is $4.60. If I have Q quarters, how do I represent the monetary value of Q quarters?
Q times 25. Q 25.
0.25 times Q. Yeah, the number of quarters multiplied by 0.25, that represents the monetary value of Q quarters. Okay, so 0.25 times Q, this, since each quarter is worth 25 cents or 25 hundredths of a dollar, then 0.25 times Q represents the monetary value of Q quarters. We add that to the monetary value of N nickels. So each nickel is worth 5 hundredths of a dollar, so 0.05 times N nickels. And the total monetary value is $4.60. Okay, now to get the other equation, we're going to use the second sentence. The second sentence doesn't refer to the monetary value. It just gives us information about the number of quarters and how it relates to the number of nickels. Okay, so something that might be helpful, use a partial translation of the second sentence. do that by using the variables. The number of quarters, that's Q. So Q is 3 more than twice the number of nickels. How do we represent twice the number of nickels? Two n, right? 2 times n is twice the number of nickels. So from here, we might be able to write down an equation. Q is the same as 3 more than 2n. Okay, I see the correct equation on YouTube. But if it's not immediately apparent how to get an equation out of that, there's perhaps something else you can do. So in this statement, it's saying that Q is greater than 2n by 3. Right? Q is 3 more than 2n. So Q is greater than 2n by 3. And we can convert this information into an equation. We can actually do it in 4 different ways. We just want one. Convert this to an equation. So since 2n is smaller than Q by 3, if we add 3 to 2n, then that will be equal to Q. Q is equal to 2n plus 3. So we can use that as our second equation. Okay, so if we use substitution, this is one of our equations. Q equals 2n plus 3. And our first equation, 0.25 Q plus 0.05n equals 460. We can replace Q with 2n plus 3. And so we get 0.25 times 2n plus 3 plus 0.05n equals 4.60. And then we can solve this equation for n. 0.25 times 2n is 0.50n. And 0.25 times 3 is plus 0.75. And then plus 0.05n equals 4.60. In the next step, we can do 2 things at once. We can add the like terms, 0.50n plus 0.05n. That is 0.55n. And we can also subtract 0.75 from both sides. And when we do that, we get 3.85. And then divide both sides by 0.55. So we get n equals 3.85 divided by 0.55. And that simplifies to 7. So there are 7 nickels. 7 nickels, the number of quarters is 2 times the number of nickels plus 3. So we can replace n with 7. Q is 2 times 7 plus 3. 14 plus 3 is 17. Okay, so 17 quarters and 7 nickels. So you can verify that those are the correct numbers. You know, if the total monetary value is $4.60, then just find the value of 17 quarters, 17 times 0.25, and add that to 7 times 0.05, and that should add up to 4.60. And the other equation, the number of quarters, is 3 more than twice the number of nickels. That also works out. Okay, we're out of time, so go ahead and sign in for attendance.